All right, so now that we've figured out how to draw our Lewis structures, what we need to do next is again kind of start thinking about our compounds and what's actually happening to our compounds and why are we seeing just a really wide variety of properties. So if we look at CH4, CH4 is methane. So methane is a gas, right? It gets released by cows in their farts, right? But we're able to burn methane for us to get energy. Conversely, right, water here is H2O, right? It's a liquid at room temperature. We can get lots of things to dissolve in it. So we have very different properties between CH4 and water, right? Same idea if we come down here to CO2, right? CO2 has very different properties, right? It's a gas at room temperature. If we blow CO2 across the flame, it's going to blow that gas out, right? But if we blow O2, O2 would be this, right? So O2, we blow that across a flame and it's going to get bigger. We blow CO2 over a flame and it's going to get burnt out, right? So these are both covalent compounds, right? These are both covalent compounds up here, but they have very different properties that we see, okay? So what we need to do is we need to start to understand a little bit more about why we are seeing those properties, okay? So if we go to our note packet, and we go to this page here, the polar versus nonpolar molecules, right? We have two different types of covalent compounds, okay? A molecule is a covalently bonded substance, always two or more atoms or elements bonded together, okay? So H2, right, would be two or more atoms that are bonded together with a covalent bond, okay? So a covalent compound is a molecular compound, okay? So when I say a molecule, we want to think about our covalent compounds, okay? So a polar molecule, right, these are polar molecules, okay? We have unequal sharing of electrons, okay? So even though we have covalent compounds, right, it still matters where those electrons are, right? With our ionic compounds, we said that the electrons totally get pulled over to one side, totally left without any on the other. Here, our polar molecules, the electrons mostly get pulled over to one side, and so we have an unequal sharing of the electrons, and it doesn't pass the mirror test, and it can't be folded to reflect itself, okay? So if we have two atoms, right, we have to have different elements, different electronegativities. If we have more than two atoms, we need to either have unbonded electrons or lone pairs around the central atom, okay? So this is how we're going to identify our polar molecules, right? So if we look at HCl, we can draw HCl, we'll give our electrons to chlorine. What we can see, right, here's our Lewis structure. We can see that we have two different atoms, or two different elements with different electronegativities. So we're going to have a dipole that we're going to draw this dipole arrow, okay? So the positive end is going to point towards our negative end. Chlorine is more electronegative than hydrogen, so the electrons get pulled over towards chlorine, okay? We have more electron density that's over on chlorine. So if we were to kind of draw our electron cloud, it would look kind of pear-shaped, where we have lots of electron density over on one side, where this would be our hydrogen, and this would be our chlorine, right? Our electrons are more going to sit over on the chlorine side than they are on the hydrogen side. So we draw an arrow from kind of more positive end, this kind of looks like a positive end, over towards where the electrons are, okay? So let's now look at H2O. If I draw H2O, right, I said to get in the habit of drawing H2O like this, because when we draw it like this, we see that H2O, right, we have unbonded electrons or lone pairs around the central atom, right? We have these two lone pairs that are non-bonded, right? And we also see that if I were to put a mirror right through the middle, right? So right through the middle there, my bottom is different from the top, okay? So it does not pass the mirror test, right? It can't be folded over and reflected on itself. Yes, it can be this way, but not this way, okay? So what we see is that more of our electron density is going to be up here. So our dipole arrow is going to point up, okay? We have a more positive end down here. Oxygen pulls on the electrons and pulls them up towards where our lone pair electrons are. So we have more electron density that's up there, okay? So if, again, we were to kind of draw our electron cloud, we would see something kind of like this, right? Where more electron density up here, this is the oxygen, this would be my hydrogen down here, and this would be my other hydrogen down here. A little bit of electron density, but more electron density up high. So we see that our arrow goes from positive of less electron density towards negative of our more electron density, okay? So let's flip over to our next page. On our next page here, right, now we're looking at nonpolar molecules. Nonpolar molecules have equal sharing of electrons, okay? Or, right, it does pass the mirror test and it can be folded to reflect on itself, okay? So if we have two atoms, right, it has to be the same element. So let's look at Cl2 here. Cl2, right, we're going to have a single bond between chlorine, and we see, okay, yes, right, there's going to be an equal sharing of the electrons between the two sides, right? They're the same element, okay? If we have more than two atoms, right, we cannot have any unbonded electrons or lone pairs around the central atom, okay? If we have lone pairs around the central atom, that's generally going to indicate that that's going to be a polar molecule, okay? So let's look at CO2 here. CO2, right, we would say, okay, we've got oxygen on that side, oxygen on this side, right? And what we can see is that we have a mirror this way and we have a mirror this way, right? The electrons on the top are the same as the electrons on the bottom. The electrons this way, right, are the same as the electrons this way. So we have equal sharing of electrons. And so that results in us having a nonpolar molecule, okay? Let's try the same thing with CCl4. If I look at CCl4, right, I'm going to draw chlorine, 1, 2, 3, 4, 5, 6, 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 plus the bond, that's 8 for all of them, carbon, 8 electrons around them. It's going to be all stabilized, and we can see again that we have top and bottom same, left and right same. So we have no unbonded electrons around the central atom, and we have a mirror, okay? So we have a nonpolar molecule, okay? So these nonpolar molecules are going to have different properties than our polar molecules, okay? So what we want to be able to do now to help us identify our polar molecules and nonpolar molecules is to identify our A, X, E structure, okay? So A, this is the central atom. We're going to start from a central atom. Then we're going to identify how many pieces are attached, okay? So how many atoms attached? Finally, we're going to count how many lone pair electrons. Okay? So, if we can get our ax, we're going to know a little bit more about whether we have a nonpolar or a polar molecule, and we're going to know a little bit more about the 3D structure. Okay? So if we go over back to our big packet, right, I'll show us how to get our ax structure for a couple of these. Okay? So first, right, if we look at CH4 here, we would say carbon is the central atom. That's the A. X is going to be how many atoms we have bonded. 1, 2, 3, 4. So we're going to do a subscript of a 4. And then how many lone pair electrons? No lone pair electrons. That's going to tell me, oh, AX4E0, that's probably going to be a nonpolar molecule. Okay? If I look now at H2O, right, oxygen is my central atom. X, how many bonds, how many atoms I have? 1, 2. I have 2 atoms attached. And then E is the number of lone pairs. I have 2 pairs of electrons. That's going to be AX2E2. Okay? The last one down here that I'm going to show, let's look at this one. Right? HCN, A, my central atom is carbon. Okay. X, how many atoms do I have bonded? 1, 2 atoms bonded. And then E, how many lone pair electrons? 0. Okay, so this is going to be AX2E0. Okay, so what we need to be able to do is fill in our whole packet with their ax structure, right? Let's get our ax.